So let me recall that there are evolving lecture notes on my website. So here's once more the address. So that's the institution. That's the group. That's about lectures, obviously. And then there's summer term 2023 HTML. So in fact, there is already now the second version of it where I added the things which I'm covering today or may cover today. So let me remind you of the fact that what I tried to explain yesterday in chapters 1 or sections 1 and 2 was that given our parabolic space-time operator and this type of nonlinear operator driven by white noise, that this problem as it stands does not make sense for dimensions, spatial dimensions larger than 2, and in fact it even does not make sense for dimension equal to 2, but that's a borderline situation. And our scaling arguments, so we did that based on scaling arguments, scale invariances in law, motivated by Brownian motion, and in this field that's sometimes called dimension counting arguments, and the two-dimensional case is kind of borderline, and but it's also on the bad side. So that's what we discovered last time, that in a certain sense the roughness of this driving of this right-hand side of the white noise is too strong for the regularizing effect of the parabolic operator in order to cope with this nonlinearity. And therefore, I already started saying that we need renormalization by changing the equation, so by introducing a counter term. And I said that this is essentially a two-step procedure. So on the one hand, you're regularizing the noise. And the nicest way of doing that, or the simplest way of doing that, and that's what I'm going to do here, is to mollify it. So, okay, so the way I wrote it was with an index rho at x. That's the convolution applied to a kernel psi r dot minus, in fact, dot minus x. And so I didn't make a sign mistake here. That's really what I want. And this should be also a rho, where psi r is defined like we did in section 2. So that's a rescaling by our parabolic rescaling operator r. In such a way that the integral is preserved. So I have to put, I think I forgot that last time, there is a minus 1 r and minus d here. Let me recall that r of x was the parabolic rescaling, which was kind of the right rescaling for this operator. So that's, in a certain sense, a Dirac sequence as little r goes to 0, which is the length scale, since by this rescaling it preserves the volume. And psi is some Schwarz function. And another way of a more informal way of thinking about this, and that will be actually helpful, is that psi rho is a mollification of psi in the sense that you're mollifying, you're averaging over translates of psi. But this is in a certain sense an informal way of writing it because psi is a distribution. So this is how you should think about it. You take this white noise, you translate it a little bit, you average over the translations, and that mollifies it, typical mollification or convolution. So now if you do that, then of course your equation now is perfectly benign. So as always, we think of the equation in the entire time space. So that now makes sense because the right-hand side is smooth. And there certainly you can give a sense to this solution manifold. Again, we're interested in the entire solution manifold. But the problem is, as rho goes to 0 and eventually you want to get rid of this mollification, the solution manifold diverges. It doesn't go to anywhere. So, so that's not enough. So what you have to do is you have to modify the equation by what's called a counter term. And so that's something which will depend on rho, but which is supposed to be deterministic. So EE independent of the realization of rho, of psi. But dependent on the ensemble in general. So the probability measure. So by a rho dependent and deterministic, what's called counter term. And the way we do it here is the following. And I will say a little bit about this now and a bit more later on. The counter term will be of this form. And you should, I didn't check it on Wiki, but I think that's the right way to see about it, that it's called a counter term because it counteracts this modification which you did on your noise. So these two things go together, they belong together, and you want to choose this counter term in such a way that as rho goes to 0, you converge to something. It doesn't become trivial, but you converge to something. So that's the art of renormalization. And of course, so now there is a priori no reason why I choose the counter term like this. I will give you a couple of hints in a second. So the art of renormalization is to, so the task or the goal is to, on the one hand, choose h of rho such that the solution manifold converges, and what that means I will explain later on, as rho tends to 0. And on the other hand, you want to preserve the symmetries of your naive solution manifold. So in a certain sense, you take this, quite successful attitude that in the end, the specific details of the equation don't matter so much, but what an equation really tells you, what matters about an equation are the symmetries. So those are the things which you really don't want to fuss with. So that's the principle. Okay, so we already spoke about symmetries last time. So I highlighted four symmetries. So there was a shift symmetry, there was the reflection symmetry, there was the parity, and then a bit more subtle, but in the end very much motivating for this here, there was a scaling symmetry, and we'll have to get back to it in a second. And so let's say I want to certainly kind of preserve the shift symmetry. So I want to preserve the property that if I shift the noise, and the law of the noise is shift invariant. So if I shift the noise, then the shifted solution is again a solution of this problem. And that will only be the case if this counter term, which a priori could be x dependent, is not x dependent, but just kind of a constant. So h superscript rho is a space-time constant. So that's kind of the first thing we do in order to preserve one of the symmetries. Now, one of the reasons why I wrote down this counter term, and for instance, not just the counter term h rho phi square, or the counter term h rho times 1, which, why should I write down this with the linear term instead of the one with the quadratic or the one with the constant? The reason for that is, if I would do that, I would destroy parity, because I don't want to destroy the fact, or kind of the memory of the fact that this nonlinearity was odd, which led to the parity of the solution manifold. So those I don't want because of parity. And another potential counter term which I could write down is a drift type counter term. So a term which would look like h superscript rho index I di phi. So first order term. But that again, even if it were helpful, I should try to avoid it because it would kind of destroy the reflection symmetry. So this one I don't want either. And we'll get back to the scaling symmetry in a while, in a bit. Okay, so that's the task at hand, right? So we want to identify this constant h, so this deterministic space-time constant h, which will be a function of lambda. So that's clear. So h of rho will be a function of lambda. So it will be a function of lambda and rho. And in fact, it will blow up as rho goes to 0. So we want to kind of identify this blowing up family of constants in such a way that the solution manifold of this problem converges, right? That's the task at hand. That's what one has to do in case of renormalization. Questions? Yes?
So sometimes in the business of solving the DDs, you want to look at the weak solutions.
Yes.
Right, and how is this related to the weak solutions? Because in the weak solutions you apply the test function of both sides.
So on the level of this equation, I don't need to appeal to the concept of weak solution because everything is smooth. When I wrote down, at some point yesterday, I wrote down kind of the linear equation with the unmollified right-hand side. And that I interpreted in a distributional or weak sense, which meant the sense I wanted to give it is by testing these distributions against Schwarz functions and by defining this here as having the dual operator act on zeta. And that's exactly the notion of weak solution. But typically then you appeal to Sobolev space or whatever. Here we're doing the weakest, that's the weakest possible notion where we just interpret the equation in distributional sense. But the problem is that the nonlinearity doesn't fit into that concept. And therefore, we have to do something much more dramatic, which, however, a priori, releases us to think even about the concept of weak solutions, because now we're in a completely smooth category. Yeah. So in other words, this, many PDE people know that the concept of weak solutions is a very kind of helpful concept in kind of dealing with giving you kind of an easy existence result, and then you appeal to regularity theory to realize that after all you got a strong solution, or in fact you're in a situation like in conservation laws where your solutions are not strong solutions, and then it's very conceptually also very helpful. It's either technically helpful or conceptually helpful. Here, that doesn't solve the problem. There's no way that this no matter how smart of a weak solution you come up with, it will not solve this problem.
But so if we solve this problem, for example, and then set lambda to 0, will it connect somehow to the weak solution of the...
Oh, if lambda is equal to 0, there's no problem at all. For the linear equation, so that's what I'm going to write down and what I want to write down in the next step. So you postulate that for lambda equal to 0, in fact, you don't need your counter term is equal to 0. If you're dealing with the linear problem, so if you set lambda equal to 0, you don't need renormalization.
But when the counter term is equal to 0, we still solve not the original problem, but the modified problem, right?
Yes, but then it converges. It converges to a solution of this problem in a distributional sense. But that's in a certain sense, so there is this consistency, but the challenge is really the interaction of roughness and nonlinearity. So although, and I will do that in the sequel, it often helps to first switch off the nonlinearity and to think about what's true there and try to think about what survives as you turn on the nonlinearity. The real reason why we want to do that is, the presence, coping with the nonlinearity, the presence of the nonlinearity. Yes?
Does the lambda have any physical meaning?
Sure. So in the quantum field literature, it's often also called a G. It's kind of something which comes from interactions in the model, which makes the model non-trivial. It then may have physical dimensions. Here, I'm already working in a completely non-dimensionalized sense, and so it doesn't carry a physical meaning in the strict sense, but it's a placeholder for many things. So, for instance, in the Kahn-Hilliard equation, it comes from certain aspects in the internal energy and can be related to this. Here, I'm just treating it as a non-dimensional parameter. In fact, in a somewhat formal way, we will see in a second. More questions? Okay, so that's really the task at hand, and in this course, I want to kind of show you how this can be how this can be done, or how this is done within the framework of regularity structures. Okay, so now there was a good question yesterday. In which sense I meant the convergence of the solution manifolds, right? So clearly, once this is smooth, it makes perfectly sense to speak of a solution manifold, and clearly, as soon as lambda is non-negative, this will be kind of a nonlinear manifold in function space. So an infinite dimensional nonlinear manifold. And the question yesterday was whether I was thinking of convergence of the solution manifold in some Hausdorff sense in this space of all functions. And that's not what one is doing. So instead, one is kind of introducing a parametrization of this nonlinear manifold, or one thinks in terms of a parametrization of this nonlinear manifold, and then shows that this parametrization converges, at least in a formal sense. So that's what I want to speak about next, so the parametrization of the solution manifold. So that's section 4. Parameterization of, so parameterization, I put the symbols into the title so that you familiarize yourself with of solution manifold. And what I'm going to say is not very deep, but important. So we're going to do exactly what I said in a second we shouldn't do, or eventually we don't want to do. Let's for a moment switch off the nonlinearity. So if we switch off the nonlinearity, we postulated here, or we agreed upon, that we want to also switch off the counter term. And then we end up with this simple equation, which is a linear equation, but there's a non-zero right-hand side, which means that the manifold, the space of all phi's, is an affine manifold. And it's nothing wrong with having kind of a picture in mind. So you have some affine manifold. So an affine manifold is always modeled after a linear space. That's what the notion of affine space means. The only difference between a linear space and an affine space is that an affine space does not have a natural origin. There's no zero, no natural zero. But we know what the linear space is. So the linear space consists of all space-time functions which are annihilated by the heat operator. So people who know Luis Caffarelli like to speak of caloric functions. So those are solutions of the heat equation, entire solutions of the heat equation, so solutions of the heat equation which extend everywhere in space-time. And now there is a very fundamental, so perhaps you're familiar with this in case of holomorphic functions which are entire, so holomorphic functions which are defined on the entire plane C, have to be convergent power series, are analytic. And the same holds true for, harmonic functions in general space dimension, and it also holds true for caloric functions. So we know that all these functions are analytic. That means they can be developed into a convergent power series with radius of convergence which is infinite, and I can do that in every point. Yes?
What did you say that Caffarelli called these functions?
Caloric.
Caloric.
Because it's the heat equation. And when you burn heat, you burn up calories. So, but that's just a name, right? So the analogy is really, you should be reminded of your complex variables course. And so in principle, we know exactly how to parameterize the affine solution manifold, namely by caloric functions, by power series that satisfy the heat equation. Now that's a little bit of inconvenient situation because, for instance, if you think of Laplace equation, which is the little brother of the heat equation, capturing or enumerating or finding a good basis for all the entire functions that are harmonic is a bit inconvenient. That leads up to spherical harmonics, to harmonic polynomials, and there would be not really a natural basis. So we want to relax the problem, but this is, in a certain sense, just for convenience. We want to say we really want to modify the equation once more, but now in a kind of much less subtle way, so that in the affine case, all analytic functions, we get an affine manifold that's modeled by all analytic functions. So for convenience, we relax our equation, let me call this star rho, to the problem L phi minus lambda phi cube plus h rho phi, let me put this on the other side, minus psi rho is an analytic function. So in a certain sense, we make our task even larger. We say not just do we want to kind of capture all the phi's which solve this equation with a mollified white noise on the right-hand side, but we're allowed, or we even allowed to change, to add an analytic function, and of course that still, keeps the nature of the problem, because a white noise is very different from an analytic function. They live in completely different worlds. This here is rough and stationary. This is extremely smooth and non-stationary. So we don't really change the spirit of the problem. But if we do this, we now may say that, where did I put the eraser? Well, that's another one. So after this change here, we now know that for lambda equal to 0, the solution manifold is affine space over the space of all analytic functions, analytic space-time functions P. So that's easier. But now we still have the problem that this doesn't yet give us a canonical parametrization. In fact, we have to choose a point on the solution manifold in order to get a parametrization. So pick a solution, and I already introduced this notation of this problem. Then we get a parametrization of the form, at least for lambda equal to 0, we can write phi is equal to pi 0 plus p, where p runs through all analytic space-time functions. So here, somewhere on this manifold, we have our pi 0, and p is a tangent vector. And this gives us now a parametrization of our solution manifold in the boring linear case. Okay, so far nothing really deep has happened. And later on we have to think about how to pick. We have to find a good rationale or kind of a way of how to pick in a natural way this pi 0, and that can be done. I'll explain that later. Okay, so now comes something which is extremely convenient to think about, and to think in these terms. So it's conceivable, or it is conceivable that this parameterization extends to the case of lambda not equal to 0. Of course, not then in this linear form. So the thing you should have in mind is that for lambda equal to 0, you have this sheet, and then for another value, for a positive value or negative value of lambda, you have your nonlinear manifold, but still you can write everything as a graph over P space, like we did, with help of this pi 0, and down here is sitting the origin of P space. So you think about that, and in fact we're going to essentially construct this this parameterization. You think of that this thing which is linear in the absence of nonlinearity survives, deforms into a parameterization in the nonlinear case. And in fact, it's convenient to really think about this as something which parameterizes all these sheets. So something which associates to lambda and p phi. Of course, this is always for fixed psi and rho. And what's going to happen in the sequel is that we're going to construct this this parameterization. Questions so far? So here what I'm doing now is it's completely heuristic. So in the end, in whatever proof I'm going to present in the end, what I'm saying here doesn't actually play a role. But on the other hand, it's, I think, extremely important because it gives you the right picture. It gives you the right set of mind and motivates what I'm going to introduce.
When you say that all p that solve LP equals 0 is analytic, does it mean in particular that all distribution p that solves LP equals 0 is actually a function?
Yes, in particular. So that's well known. I don't know how much of PDE you encountered, but that's well known for harmonic functions. If you have a harmonic function which is weakly harmonic in the sense that it solves the Laplace equation in a distributional sense, or in the sense that it just satisfies the mean value property, there is an easy argument, which for instance you would find in the book of Craig Evans, that these functions are actually infinitely smooth, infinitely often differentiable. And in fact, a further argument shows you that they can be developed into convergent power series. So that's regularity theory, which again, that's standard, I would say, standard classical 20th century, perhaps even 19th century regularity theory, which we're not actually going to use in what we're going to do later on, but I think which gives you the right set of mind here. More questions? Yes?
So for the equation on the right-hand side, is it always possible to find pi 0 even when the right-hand side is not?
That's a priori not clear, but in fact, in a certain sense, we're going to construct it. But on the other hand, you shouldn't be, too surprised because this is a linear equation. So in fact, existence is not a difficulty. The more interesting question is how can you choose a canonical solution? Because in the end, we want to find a natural parameterization. Everything which I'm going to tell you in the next hour or so, or perhaps even in the next session, is about how to do things in a canonical, in a natural way. So, so therefore I'm telling you, don't worry, you know, existence is no problem, but what you should be worried about, how can you do that in a natural way? And that is something which I haven't told you yet. More questions? Yes?
I mean, in our initial equation, the lambda is fixed, but here you let the lambda vary, so is there a reason for that?
It's, yes, that will become apparent in a second. It turns out, and that's also a little bit in the spirit of rough path of Lyons, it's in a certain sense natural to consider all nonlinearities at once, which here means all lambdas at once. It's a liberating thought. Of course, here it looks like a card player's trick, but in the end, it will be. It's an extremely important thought. More questions? Okay, so now let's try to get this this idea to work. And the way, again, following the math physics literature in a way we read it, is to make the ansatz that this parametrization can be also developed into a power series. So that's the next section. So a power series representation that will give rise to objects pi beta, c beta of the parametrization lambda p goes to phi. So what I'm going to do now, in kind of next half page, is to introduce coordinates on parameter space. On what I want to be the parameter space. Okay, so parameter space was really R, which is lambda cross analytic functions. And of course, the second part is the interesting part. What are natural coordinates on the space of analytic functions? Well, the coefficients in the power law series. So it makes sense to look at the following coordinates, and I will use z's to denote coordinate functions of P, which is defined as the nth partial derivative of P in some, at this stage, completely, or not just at this stage, but kind of some arbitrary singled out origin of space-time with a combinatorial factor. So this here is just what you think it should be, ni factorial. And n, we have already seen it, is a space-time multi-index, so it's something in this space. That's clearly kind of the right way to put, or one right way to put coordinates on the space of all analytic functions, because those are just the coefficients in the power series expansion of your function P. So that's a natural way to do to introduce coordinates. But again, there is no reason to endow space-time. Already Galilei understood that there is no natural origin for space-time. So if you write 0 here, this is a kind of an arbitrary action. And I'm stressing this because it will get back at us. So the fact that we somehow arbitrarily choose whatever Paris to be the center of the universe will get us into problems eventually. So therefore I make this remark. Okay, so those are coordinates on P, and then for some, for some strange consistency reason with other papers, I'm going to write the coordinate on the, I'm introducing also coordinate on this component, which I call Z3, and the 3 is a reminder of the cubic nonlinearity. Okay, so that means now we have coordinates down here, and here, if you want, is lambda. So we've put coordinates here, and now we make before we do that, let me also introduce one last notation, which is the notation of a monomial. So now comes an important concept, namely the concept of a multi-index beta. So this is something which associates to the disjoint union of these two index sets. So 3 disjoint union with this here. A non-negative number, a non-negative integer, in such a way that that in most cases, in all but finitely many cases, you associate a 0. And if you do so, you can define a monomial. So the monomial Z beta is then defined as Z3 to the power beta 3 times the product over all n's 1 plus d of Zn beta n. So that's a kind of a monomial in these coordinates. And because this here is a multi-index, this product, which looks like an infinite product, in fact is just a finite product, because most of these exponents are equal to 0. So it's like, the only difference is, I'm sure you're used to the concept of monomials in RD. The only difference now is that you have an infinitely many coordinates. So therefore, I have to be slightly more careful by saying that beta is a multi-index in the sense that beta 3 plus the sum beta n is finite, which means that most of these entries are equal to 0. Okay? So this is, I don't know, I never really took a serious course in algebra, but this is, of course, kind of probably the first thing you do in some algebra course. So why do we do this? Because now comes the most important line. Because we make the ansatz that the counter term, which is supposed to be a function of lambda, can be developed in a power series in terms of lambda, which I now write in this somewhat overblown way. But more importantly, and that's really the crucial point, I want to write phi, I want to write this parameterization in the very same way. And now it's a sum over all multi-indices of Z beta lambda p times pi beta. Sorry. Oh, downstairs. where this here is a random space-time function. And at this stage, this is a completely formal ansatz because this sum in general is infinite. And it's truly infinite. So the ansatz is completely formal at this stage. Right? But it's a very important ansatz. You want, in a certain sense, to algebraize this idea of a coordinate of a parameter representation. So you lift it, you introduce these already pretty algebraic looking coordinates, and you write your parameterization in this formal way as a power series in these infinitely many coordinates. Right? That's so there's a lot of things going on here. In a certain sense, it's a separation of variables where you isolate the parameter dependence in these monomials, and you on the one hand, and the space-time dependence and the randomness in the other factor. So it's like a neural net, right, with infinitely many internal nodes where you paste something in and you get something out, or like a plug in a socket. So the goal, so what's going to come is that, in fact, so in principle, all these things should be indexed by rho. Let me do this once here, because the solution manifold depends on rho, so this should depend on rho. And in particular, this should depend on rho, and we expect these things to blow up as rho goes to 0. And the big task is to show that these things don't blow up as rho goes to 0. And that's the goal of the course, to convince you that if I adopt this perspective here, I can give a sense, I can characterize these coefficients, and I can figure out that they're under control, that they don't blow up. Other questions? So this is kind of really perhaps the most important concept of this course, to understand this formal power series representation, which is kind of a very lavish way of encoding this entire solution manifold in this formal representation. Yes?
Very basic question, but wasn't rho a constant?
Sorry? Rho was this convolution, this modification scale. So rho was psi was coming in form of this psi rho. Rho is indeed a constant. It's a length scale, but I want to send it to 0 because I want to get rid of my modification of my convolution of this regularization parameter rho. Rho denotes.
The definition of Cn rho looks like rho is a function.
Where do you see another rho? That's p. Sorry. So this is rho, and this is p. But I also recommend to look at the nodes, because my handwriting may be, in the notes that should become clearer. So rho is, I will always use the letter rho to denote this completely artificial regularization parameter which I want to get rid of. That's the task, right? I want to get rid of the regularization parameter, and I'm realizing that I have to introduce this counter term into the problem in order to compensate, to counteract the vanishing regularization. And the counter term now I expand in powers of lambda. That's not deep. That is a natural ansatz, and it only starts at k equal to 1 because I postulate that the counter term vanishes if lambda vanishes. But the much deeper thing is this here. So please do ask questions. Yes?
Yeah, perhaps I'm showing my lack of knowledge of the field, but is this something an expert would look at this problem and think this is a good way of looking at it, or this is a very out of the blue, weird thing?
So I think, and some people here know that as well as I do, this way of writing something came actually up in numerical analysis of ODE schemes, where lambda would be replaced by general nonlinearity, which defines your ODE, and you want to write the solution for general nonlinearity. So this type of this type of series, and in this case it's called Butcher series. And so I think this way of algebraizing a problem, an ODE or a PDE problem, is not completely strange. And it's also in the spirit of I'm often mentioning these rough path approach to stochastic differential equations by lines, which in a certain sense does something very similar. And the model, so this is what in Heira's language would be called a model. The model in a certain sense can also be interpreted in this way. But now this is a little bit, I would say, our take on it, but the experts, I don't think, are surprised by writing this down. But you have all reason to be surprised. I mean, I was surprised when I saw it. Yes?
So one could interpret Z beta as basis of the non-linear manifold.
So the way I would interpret it is rather like this. So you have this parametrization, and now you take all possible partial derivatives in the origin. So these here are partial derivatives of your parametrization in direction of a certain combination of your coordinates. So in that sense, it's related to the coordinates, but it's related in this infinitesimal way that you say, I just want to understand in a certain sense the germ or the jet of these coordinates in the origin. So I think it's a little bit dangerous to say that that these objects would really kind of parameterize the nonlinear object. They just do it in this infinitesimal way. Very much like what we're doing here, that we're saying we describe a nonlinear function in the large by its derivatives in one point. That works because it's analytic. Here, this is completely formal. We're very far away from an analytic situation in this sense, in this infinite dimensional sense. Still, it's extremely helpful to adopt this perspective. More questions? Yes?
Just to be sure, the definition of H rho, it's you can replace Z3 of lambda by just lambda.
Yes. So the reason. So here I'm here this notation is completely overblown, but I need it here because here it feeds into the definition of the monomial. And then in order to put both on the same footing, I'm using this overblown notation here, although I really just need it here. More questions?
I would like to ask if two different analytic functions will have the same representation in your
Here?
theories? Yeah.
No, that's I think in complex variable theory it's called the Identitätssatz. Actually, I don't, since I learned it in German, I don't know. So if P is really analytic, then there is a one-to-one correspondence between this sequence and the P. And one-to-one linear correspondence. So here this in fact is not really formal. This is rigorous. Let me rather use the word informal. So this is not informal, whereas this here is completely informal. So I want to use the word informal because in a second I will introduce the notion of formal power series, which are not informal. So I prefer to use the informal here to make sure that when I say informal, I mean something that doesn't correspond to rigorous mathematical statement here, because this sum will not converge, but still it's very helpful to think like this. More questions? Yes?
I guess I don't really see why it's important that these coefficients came from an analytic function. Is that
No, you can forget about it, but I think it's so the realization that the homogeneous equations of whatever PDE problem there was, as I said at the very beginning, L, you can think of L as, a more general elliptic or parabolic operator. And what's, in a certain sense, very much inherent to this entire theory is that solutions of the homogeneous problem are analytic. If you would do the same thing for the wave operator, the story would be completely different. And although you could, say, I can do exactly the same thing, it wouldn't lead to anything useful. So although in the end, what I'm doing here is just, is just serving as a motivation for writing down this series, I think it's in a certain sense an honest motivation. There was a question here.
By setting lambda equals 0, is it possible to find out who pi is by studying the homogeneous problem?
So that's exactly what we're going to do in a second. I'm going to so now the task at hand is to collect all conditions we need on these coefficients so that this thing indeed is a solution of our problem. And then that in fact these coefficients are uniquely determined, and then that they can be estimated in a way that's uniform in rho, and then, but that is something which I will not do, that in fact they have a limit as rho goes to 0. So that will come now. So now the next the next hours I will be busy with telling you what the conditions on this on these pi are, and you will perhaps not be so surprised that there is a hierarchy of a kind of nonlinear relations and linear PDEs which will characterize these coefficients, and they can be in a certain sense solved inductively, and then we have to analyze how whether indeed we can solve them in such a way that things stay under control. More questions? Yes?
The expression of where phi here, I guess it's a kind of linear algebra. So which function is?
So here I'm really thinking. So it's reverse engineering. I want to construct this map, right? I want to construct this parametrization, and I make this ansatz right here. Now I have p and lambda. So this defines phi. If this thing would converge, which it doesn't, this would define phi as a function of lambda and p, which exactly serves this purpose.
But you say it's a solution. The phi is a solution.
Yes. So this is why we get conditions on these coefficients, right? So this is.
A coefficient.
Yeah. So this is this is not different from this here. It's just an infinite dimensional version of this, where on the one hand you have coefficients. Sorry, on the you have these objects. Now I'm not actually I'm not sure whether I do this the right way, but I think I do, and on the other hand, you have these things.
So that's a basis function.
Those are generalized monomials, right? These are these are space-time monomials. These are functions of space-time. These are functions of space-time, and in fact, there are also functions which are random, because there is the random right-hand side behind everything. So the analogy is that
To have switched the red and the yellow, I will have the feeling that x to the n is the
Yeah, probably you're right. Probably you're right. But the fact that, I mean, it's a little bit a matter of taste. But the fact that you also are able to think about it the other way around means that you're getting familiar with it. So let me not too much insist on this. I mean, I think what's more important to think about that this is a separation of variables. Here is the P, here are the parameters, the nonlinearity, and this parameter space which you decided to take. And here is space-time and the randomness. More questions? Yes?
As you take the modifier rho to 0, you're losing regularity, but you still have this Taylor expansion thing.
Yeah, but P is not the solution on which I lose regularity. P is the parameter. So this here is not affected by rho, right? The rho dependence also gets isolated and it's just sitting here. So as long as rho is positive, those are smooth random functions, and as rho goes to 0, those will become random Schwarz distributions in space-time. More questions? Okay, did we exhaust all questions? That's good, but I think it's good that you ask questions because this is now, this is probably the kind of the crucial moment. Okay, so there's one easy thing I should say here based on this representation, which also so I think the people from statistics should like this because it's fairly abstract and high dimensional, and so in a certain sense, the spirit of what I'm doing here is actually forget about the PDE. Yeah. So also that's something which people from statistics may like. So we combine two things for a moment. So we postulated that in the previous section we postulate, or perhaps not in the previous, but in this one, we postulated that in the case of lambda equal to 0, we want our parameterization to be simple. And well, on the other hand, we postulated this form here. Let me write it down again. And now, for internal consistency, these two things have to be compatible. And from this, we learned something. We already learned that some of these coefficients are determined. So, for instance, if we have a multi-index for which the beta 3 component vanishes, which in a certain sense corresponds, which is only if lambda is equal to 0, only these multi-indices survive. Not equal to 0. We learn that this is equal to the monomial for beta being delta n. I'm going to explain this in a second. Or 0 else, provided beta 3 is equal to 0 and beta is not equal to the 0 multi-index. So there is, in fact, so therefore probably the color coding which I used before was not completely wrong, because from this we learn that these coefficients here, these generalized monomials do contain the standard monomials for specific choices of multi-indices. And by delta n, I mean, so delta n denotes the multi-index with the property that delta n of 3 is equal to 0 and delta n of m is equal to 1 if m is equal to n and 0 else. So it's in a certain sense a Kronecker, one of the very simple multi-indices, which just associates a single one to one of the entries, namely to the entry which corresponds to the space-time index n. Okay, so that's a remark. You can. It's a good exercise to ponder about it, why it's true, or why it should be true. And now we come to what. When do I have to stop? 12:30. Okay, so now we come to. So here, this just kind of characterizes a very small fraction of the multi-indices of the beta pi's. Now we come to the most to the next important business, namely writing down, trying to characterize these coefficients, writing down PDEs for these coefficients. So that's what happens in the next section. Perhaps I'm going to leave this here. Perhaps. So n will always, if I don't specify it differently, will always be a space-time multi-index. What else? So those are a couple of relevant definitions. So then I can start erasing this. Okay. So now comes another bookkeeping trick. So section 6, characterization of pi, and I will also introduce a pi minus. And there will be formal, and now formal means, sound, formal power series. So I have to introduce a bit of language. So we interpret this collection of coefficients, which a priori is, a big bag of coefficients. We give them a nice interpretation. And now, again, I didn't take any serious algebra course, but I'm using this notation. So these coefficients are in the space X, which are random, which is the space of random space-time functions. At this stage, smooth functions. And now I want to interpret these coefficients as in fact defining what is called a formal power series with coefficients in this space and with the dummy variables which were given. So this at first is just a notation, and the notation in a certain sense asks us to completely forget about where these variables come from, that they have this meaning, but just think of them as being dummy variables, which of course commute, and then we have kind of coefficients in the formal power series. So this is the space of formal power series in the dummy variables, infinitely many variables, Z3, Zn. With coefficients in X. So why is that a nice structure, or why is that convenient, at least in terms of writing things up? Because if X is an algebra, and of course random space-time functions are an algebra, I can multiply two space-time functions, I get a space-time function, and if they're random, the product will be random. So if X is an algebra, in fact also this space is an algebra. So which means I can multiply. I can not just add and scalar multiply, but I can multiply two elements. And the rule is very simple. So pi of beta bar is just the sum over all pairs of multi-indices. So the product of pi and pi prime, the beta component thereof is given, or the beta bar component thereof, is given by this, the sum over all tuples of multi-indices beta, beta prime that add up to beta, and then I'm taking the component-wise product. Right, and that's the right. So if the pi betas were coefficients of an actually convergent power series, then this would correspond to the coefficients of the actual product of the two convergent power series. But the nice thing is that formal power series can also be multiplied, although they don't live in, there is no function behind it. Still you can work with them as if they were functions because of this, at least when it comes to multiplication. And here, when I said functions, I didn't mean functions, space-time functions, but I meant functions of these dummy variables. So that's very convenient, because now we can, equipped with this, we can write down the hierarchy of, yes?
Just kind of vocabulary. In this context, is algebra any different from ring?
That's a good question. I'm not so here, in fact, you can here for these power series, you have many inverses, but so I think ring just have a you're questioning my algebra knowledge. So ring just has a multiplication, no addition, right?
No, it has addition. Maybe algebra is when you are considering a basic field. For instance, it's an algebra on R, and you also want to have a notion of scalar terms, maybe.
Yeah, I think that's good. Yeah, I think that's it. So here it's an algebra in the sense that I also have scalar multiplication. So it's a vector space with a multiplication. Yeah, I think that. Okay, also, but that's just aside. These these coefficients of the counter term, of course, I can also think of them as a single object, which then would be something which is a formal power series in this dummy Z3 variable with coefficients in R. And of course, I can think of this as being embedded into my big space of power series because R is a subalgebra of X, and this is a subset of these coordinates. That's convenient also for writing down what I'm going to write down in a second. Yep.
This maybe is just a continuous rotation. So because here we have like I think beta used in like for two different meanings, right? Because in this sum we have beta plus beta 3.
Oh, sorry, there's a beta bar missing here. Perhaps I should call it just gamma.
Right, and also in the line above, right? We have this pi and we have this beta indexed twice. What's the meaning?
Where?
Below the interpret, yeah, here. So you have beta used as index twice.
Well, I mean, here this is, that's just perhaps not your favorite notation, but I'm saying that I want to consider this family indexed by beta.
Oh, I see.
Right, a priori it's just a bag of functions, a bag of random space-time functions, and I want to give them this structure. Yes?
How do I think of this space X as this very generically just all possible stochastic processes on this set, or
so eventually of course we'll have to measure the size of objects in the space, and then I will get much more concrete, but for the purpose of this heuristic discussion, just think of it as space-time functions which are random. And that's an algebra. But as soon as I start putting a norm on it, then I get problems with multiplication because, as you know, the product of two Gaussians doesn't have Gaussian tails anymore. And so therefore I avoid this by just saying those are random space-time functions. Yes?
Sorry, again a question. So this capital pi with no index,
Yeah.
and the fact that you can multiply it, somehow it represents phi. The way you multiply it represents the way you would multiply
Exactly. We'll get to that in a second. That's exactly the point, because now I'm claiming that the informal translation of the PDE we're interested in, L phi minus lambda phi cube plus h rho phi plus psi rho is equal to an analytic space-time function, that this translates into the following: L pi is equal to Z3 pi cube plus C times pi plus rho times 1 is an analytic function, component-wise. And this here I will give a name. I will call this pi minus. And that's exactly what you were saying, that the product on this space of formal power series is just representing the usual product on the space of functions. And lambda was being represented by this dummy variable Z3. H was being represented by C. I told you that C can multiply the pi. And 1 is just the unit element in the algebra. So the beta component of 1 is equal to the constant function 1. if beta is equal to 0 and 0 else. Okay, so
Sorry.
yes?
There is a word I cannot read, just above analytic function.
Component-wise. So for every beta component, it's an analytic function.
So there may be something you want equal instead of minus. Probably L pi minus.
Sorry. Yes, so plus. Thank you. Okay, questions. That's let me write it down. What this means component-wise, so that it becomes perhaps again a little bit less mysterious. And then let me write down some examples and then I stop. So component-wise, this means that pi minus beta is given by a sum over triples, delta 3 plus pi 1 plus pi 2 plus pi 3 is equal to pi beta 1, pi beta 2, pi beta 3, plus a sum over doublets, pi 1 plus pi 2 is equal to pi, and pi 1 of 3 is not equal to 0, whereas pi 1 of n is equal to 0 for all n, of c beta 1 pi beta 2 plus psi rho delta beta 0. So that's what it means spelled out. And now you see that it's convenient to have this compact notation because it frees you from writing down these expressions every time, but mathematically it's exactly the same. And let me give you a couple of examples to show that this hides a certain complexity. So of course, pi minus 0, if you put this as a 0 index, it never contains a del 3. It never contains something that's non-zero. So pi minus 0 is just psi rho. Pi minus delta 3 is the first non-trivial thing. So from this identity, you see that all these three betas have to be equal to 0. So you get pi 0 to the power 3. Pi 0 was our, at this stage, arbitrarily picked solution of the linear problem. But you also get something from here, which is c 1 times pi 0. What else did I want to say? Since I wrote kind of 20 minutes ago on this blackboard that pi del 0 is equal to the constant function 1. That was kind of the case of purely polynomial multi-indices. We get that pi delta 3 plus delta 0 minus is given by 3 times pi 0 square plus c1, pi delta 3 plus 2 times delta 0 minus is given by 3 times pi 0, and pi delta 3 plus 3 times delta d0 is again pretty trivial. It's equal to 1. And but then it starts getting more and more complex, and kind of combinatorial factors come up, which are important. So pi minus 2 delta 3 is equal to 3 times pi 0 square pi delta 3 plus C1 pi delta 3 plus C2 times pi 0, pi minus 2 times delta 3 plus delta 0 is equal to 3 times pi 0 square pi delta 3 plus delta 0 plus 6 times pi 0 pi delta 3 plus C1 pi delta 3 plus delta 0 plus C2. So you see that if you continue this list, this nicely looking identity in fact hides a lot of complexity. So that's the main reason for introducing this, this setup, that it's a good way to organize an increasing complexity. But at the same time, you may see that this really looks like a hierarchy, right? So here you get the right-hand side for the 0 equation. That determines pi 0, which, forgetting for a moment of the counter terms, gives you the right-hand side of delta 1. Then you solve, delta 3, then you solve for delta 3, which will help you when you go here, because you need the delta 3 here. And when you go here, you also need the delta 3 plus delta 0, which we get from solving this equation, and so on. So, not surprisingly, these things have a hierarchical structure, and in fact, you construct them kind of in terms of an induction. But the induction order is somewhat non-trivial, and I will not get to it at this stage. But so I think I have to stop. But what's going to happen next is, so we're going to never work on the level of these more and more complex looking equations. We'll always stick to this neat and abstract form. And what comes next is that I have to tell you how to uniquely solve the equation, how to uniquely invert this operator L, so that this here really becomes a construction. And in order to do so, we have to revisit the homogeneity, but this time for the nonlinear problem, so that will become more interesting. Once we revisit the homogeneity, I can write down reasonable conditions which ensure that these equations have a canonical solution. And once I have this, I can construct the pi's, and then I have to tell you how to canonically choose these counter terms, these constants. So at least the next session, I will be busy with telling you that although this looks like this did look like a completely crazy ansatz at the beginning, it in fact seems to be the right ansatz, because there is no degree of freedom anymore. It really gives you an algorithm. It defines an algorithm how to define step by step these coefficients. So that's what I want to convince you of next. And then eventually, of course, the big goal is to estimate these things, and that's where we're going to use Malliavin calculus and so on. But in a certain sense, I have to first to tell you this stage. Okay, let me stop here and take your questions.